Okay, this is your exam 1 review 2020. Question 1 says how many hydrogen atoms are in the structure below. So you need to know that every carbon must have 4 bonds if the carbon is not charged. Where there's a triple bond, there's actually a carbon in there, and there's a carbon at the end, and you want to show the 4th bond of the hydrogen. Okay, so this one right here at least shows you the hydrogen at the end, which was the catch. Here I have 3 bonds, so there must be a hydrogen. Here there must be a hydrogen. Of course, here there must be a hydrogen. And each of these carbons on the ring must have hydrogens. So I hope by now you're counting them. And the answer should sum up to 14 hydrogens. Okay. There's 11 on the ring, 12, 13, 14. There's no hydrogen right here. So the answer here was 14. Let's look at question 2. I need question 2. So here is question 2. What is the major organic product of the reaction below? The key term here is Macovinic of addition. So the H goes where there is more across the double, which is this place. The Cl should go where there is less, which is here. So basically, without even drawing the mechanism, I know that I should end up with 2 hydrogens over there. And you can pretend that this hydrogen right here is this hydrogen that was added there. And then the Cl will go the other side. With mechanism, this is what happens with the mechanism. So first, you use the pi bond, attack the hydrogen. Cl good leaving group, it goes. So you're gonna end up with this structure. So the hydrogen adds where there is more, and then the other carbon will be positively charged. So this hydrogen is gone there. Now you have a plus charge here. Now remember, the Cl fell off. So the Cl is going to come back as a nucleophile, attacking the positive center because opposite charges attract. And then you will definitely end up with this product. I don't need to draw it again. You end up with a product which happens to be product labeled B. If I don't show these hydrogens, that's your B. Okay. Sweet, sweet, sweet. Now let's continue. Let's look at question 3. Let's look at question 3. It says, what is the abbreviated noble gas electronic configuration of a phosphide? Phosphide is the catch. This simply means this is an ion of phosphorus. That's what a phosphide is. So knowing that, we know phosphide is a nonmetal, so it reacts by gaining. P, the phosphorus has atomic number, we use Z. It has atomic number of 15. So I can write the neutral electronic configuration, which is 1s2, 2s2, and then 2p6, right? Those are 10 electrons are counted for. Then 3s2, and then 3p3. That accounts for the 15 electrons in phosphorus. But now it's a nonmetal. If you check the periodic table, you will see that phosphorus is right here. Actually, it's 3 steps away to argon. So it should react by gaining. Obviously, you see that these guys, okay, the first shell is full, the second shell is full, but the third shell is not full. Remember, we We call this a valence shell or valent shell. It's not full because the p in the third shell is not full. You have 5 electrons, you are 3 electrons away to 8, which is an octet. So the phosphorus should react by gaining 3 electrons, and you get P3 minus because it gains. Use the negative, and that's what you call a phosphide. So if P gains 3 electrons, you're gonna have 1s2, 2s2, 2p6, okay, 2p6, then 3s2, then 3p6. Now notice now the p is full, so the third shell is full, the second shell is full, the first shell is full. It's stable, and if you count all this, count all those electrons, turns out that you're gonna end up with 18 electrons. Go back to the question. It says what is the abbreviated noble gas electron configuration? This is actually the same electrons found in argon. Okay, so that will be the answer. That's the noble gas electronic configuration. Well, this is a complete electronic configuration, so we are looking for the noble gas. Okay, that's the noble gas electronic configuration. The answer is B. Okay, clear enough. So we go to the next question, number 4. Question number 4 states, where are you? Question number 4. How many valence shell of electrons are in krypton? Okay, this is simple. If you can know the period of krypton, you're gonna know its valence shell electrons. So it's in the 4th period, so it should have 4 valence shells. Okay, so the valence shells are just the ring. Like if you are to draw the structure of the atom, you're gonna draw 3 rings outside. Okay, so this is 1, 2, 3, 4. Look at the periodic table. Let me expand this. So you see krypton is right here on the 4th period. So it should be having 4 shells around it. Should be having 4 shells around it. Okay. So next, what is the total number of valence electrons in ethyl methyl ether? That compound is called ethyl methyl ether. It's an ether. We're going to count its total number of valence electrons. This is question 5. So I see that I have 3 carbons. I see that I have 10, not 10, I have 8 hydrogens. I also see that we have 1 oxygen atom. Now the thing is, for each carbon, you're gonna have 4 valent electrons because it belongs to the 4th group of the periodic table. For each hydrogen, you're gonna have 1 valent electron. It's in the first group, first column of the periodic table. And then for each oxygen, you're gonna have 6 electrons. It's in the 6th main group of the periodic table. So we're not summing yet. This will give us 12 electrons from the carbons, and then you'll have 8 electrons from the hydrogen, and then you'll have 6 electrons from the single oxygen. Sum these guys up, the answer is gonna be 26 total valence electrons. All right, that's what the question wanted, and the answer is B. Okay, moving on. What is the formal charge on the arrowed carbon? Formal charge on the arrowed carbon, question 6. All right, so that's the structure, and then we have a lone pair here. The lone pair means that's a bond that's missing, so I should be having some three, not really three, I should be having two. I should be having two hydrogens, because I said carbon must have 4 bonds on it. If we have a negative charge or a positive charge, you're missing one bond. That's quick to tell. Okay, so let's find the formal charge. Remember the formula? Formal charge equals to number of electrons on number of valence electrons. So I should say valence. Number of valence electrons on neutral atom. There are so many versions of this formula, but I think this is what we discussed. And then you subtract the number of lone pair electrons, and then you subtract half number of bonding electrons, which is just number of bonds around that carbon around the atom in question. Okay, so in our case we have a carbon. That's a carbon. Carbon is in main group 4, so it should have a valency of 4. You have 2 electrons in the one lone pair, so number of lone pair of electrons is 2. And then we have 3 bonds, which is 6 electrons, so we have to do half of 6 bonding electrons, which is the 3 bonds. Each bond is 2 electrons. So we get 4 minus 2 minus 3. The answer of the formal charge Fc will be equal to negative 1. So that's why the answer was D on question number 6. So let's move on with question 7. What is question 7 saying? Question 7 is asking us which of the following molecules has 3 electron domains around the central atom. Just a review on electron domains. What are the electron domains? We said it could be a sigma bond. Okay. It could be a pi bond. Yes, pi bond is 2 bonds, but it's taken to be 1 electron domain. Or it could be a lone pair. Yes, lone pair has 2 electrons, but it's taken to be 1 single electron domain. Or it could be a triple bond. Yes, triple bond has 6 electrons in it, but it's taken to be 1 electron domain. So which one has 3 electron domains? So we have to draw the Lewis structures of these guys to tell who is the answer. So for A, if you draw the Lewis structure, I'm not going to go through all the steps. This will be the Lewis structure for A. So which of the following has 3 electron domains around the central atom? So let's look at the central atom is nitrogen. The lone pair is 1 electron domain. The 3 bonds each are 1 electron domain. So these guys has 4 electron domains. So turns out A is not the answer. We are looking for one with 3 electron domains. So for B, if you draw, it's going to be very similar to A. So you still have 4 electron domains. Okay. You still have 4 electron domains on the nitrogen. And then for C, this will be the structure for carbon dioxide, the Lewis structure showing all lone pairs. The central atom here has 2 double bonds across. There's no lone pair. So this is 2 electron domains. Okay. And then for D, that's formaldehyde. By now you know its structure because you did the chapter on aldehydes. Anyway, you follow the steps that we followed in the first 3 chapters. You'll find that this is a structure. And now you have a double bond and 2 single bonds. This guy has 3 electron domains. So that's the answer. So this is the answer. These two are not, these three are not. Okay, moving on. So we are on question 8. Which of the following has tetrahedromolecular geometry? Select all that apply. So for A, it's gonna look like this if you draw it correctly. One hydrogen away, the other one towards. Okay, so again, we know the definition of molecular geometry. You'll have to be connecting the you connect the atoms, not the bonds. Okay, so you see, this looks like a Tetra Pak. Tetra Pak will have this kind of shape in 3D. Okay, so the bond back there. Oh, we had to connect even the one in the middle for it to look like a Tetra Pak. So these are the outsides, and there's a bond right in the back. And again, in between you do have a carbon, so you'll have to connect all those guys in between. So that's a Tetra Pak. So the answer is A. This is tetrahedral. It's not a pyramid. Don't confuse it with a pyramid, because here you have a central arrow surrounded by 4 of them. That's tetrahedral. If you are to look at CO2, where is it? I want to draw CO2. CO2 is linear. That cannot be the answer. Okay, that's linear. Molecular geometry, if you connect these elements, you'll find that it's a straight line. Molecular geometry, straight line. And then trichloroamine. Now here you don't have an element on top of nitrogen, so if you connect it, it's definitely gonna be a pyramid. So the molecular geometry for this will be like this. Okay, and that's a pyramid. Pyramid. That's a pyramid. There's a line at the back. You see, it's different from a tetrahedral, because for tetrahedral you have a central arrow. So C cannot be the answer. And then, of course, to finish off, hydrogen sulfide, D, H2S will be like this. Okay, so this one is bent. It's gonna take a V shape. Molecular geometry will be bent. Tetrahedral geometry connecting the lone pairs will be tetrahedral. For the electronic geometry will be tetrahedral, but you're looking for molecular. D happens to be bent like water. Okay, moving on to question 9. Where is 9? Which of the following has a linear electronic geometry? Obviously, B will be tetrahedrous, D will be trigonal planar. So the answer is A and C, because if you write hydrogen is gonna be like this. CO2 again is straight line. The bonds are the ones having electrons. The electrons are in a straight line. Here they have 2 electrons in the straight line, so that's linear. But for, okay, so this was A and C. Those are our 2 answers that you will select. But if you look at B, for electronic geometry, the bonds will give you tetrahedral structure. There's no lone pair in the middle atom, so both molecular and electronic geometry will be tetrahedral. Okay, we are looking for linear. And then if you look at D, we already did D. For formaldehyde, we say that it has 3 electron domains, which means most likely it's gonna be trigonoplanar. Okay, trigonoplanar. If you get something having 3 electron domains, it's either gonna be bent or trigonoplanar, but here we don't have central lone pair, so it has to be trigonoplanar, which means around the carbon it's flat. So let's do number 10. Okay. Number 10. Consider the molecule PCl3 to answer the sets below. What is the molecular geometry? It's simple. You should write its Lewis structure to answer the question. So molecular geometry, we are connecting the elements. So again, we don't care about that lone pair. So it will turn out to be a pyramid, and the pyramid has 3 elements at the surface. So this answer for A is trigonopyramidal. Okay. And then what is the hybridization of central element? Obviously, on here, we have 4 electron domains. The hybridization that has 4 orbitals mixed is sp3. 3 p's and 1 s. Those is 4 electron domains, 3 bonds and a lone pair. Okay. So trigonopyramidal, sp3. So up to that point, I can take out option A. I can take out option C. And then I'm left with, okay, I can take out even D because it's not sp2. And I can take out E. So I'm left with option B and F. Okay, here it says trigonoplanar, so B is out. So the answer must be F. Just based on these two, trigonopyramidal and sp3, by elimination, I can already say the answer is F. But let's continue. What's the approximate bond angle? Since it's sp3, bond angle will be approximately be 109. Like in between these two bonds, it's most likely gonna be 109. Okay, because of hybridization of sp3. If it's sp2, bond angle is 120. If it's sp, it's linear, is 180. What's the electronic geometry? Oh, the electronic geometry, now we consider the electrons in the bonds, we consider the lone pairs. There are 4 electron domains, so that goes with tetrahedral. Whenever you have 4 electron domains, most likely you are tetrahedral. The electronic shape should be tetrahedral. Okay. Next, the question is whether it's polar. Yeah, it's polar because the molecule does not have dipole moments cancelling, and you have a lone pair up there, so which means electrons will much reside here. This part is negative, more negative. That polarizes the molecule. All right, so I've explained question 10 too much. Let's look at question 11. Use a different color for phase difference. Okay, question 11. This is a drug called quinalaprine. It's used to treat high blood pressure and heart failure. Its structures as shown. What is the hybridization of the nitrogen on quinalaprine? So we are looking at the nitrogen marked B, not this one, but this one. So if you look at it closely, you will find out that there's 3 bonds. Okay, so let's just zooming in on the nitrogen. There's a hydrogen for this to be octet, there must be an implied lone pair. That was the catch. So the question is to determine hybridization. So you have 4 electron domains, 3 bonds, and a lone pair. So I know there are 4 electron domains. The only hybridization that has 4 electron domains has to be sp3, just like we did right here. We ended up with 4 electron domains. Okay. Now let's look and see. Next question. Rank from shortest to longest bond. This is simple. We said that alkynes will have the shortest. Triple bonds will have shortest bond, and single bond will have longest, followed by double bond. So the answer will be C is longer than B, single bond is longer than double bond is longer than A. We are ranking from longest to shortest, so the answer here is C. And then 13, arrange the following from the least polar to the most polar. Okay, so which one of the following will be the best arrangement? Let's find the least polar. The least polar most likely should just have the London dispersion forces, and most likely that's gonna be one that has the dipole moments cancelling out, or an alkane. There's no alkane here. Let's see. Yeah, let's draw the structures. We're gonna find out. So you see, that's CO2. For polarity, we consider dipole moments pointed towards the more electronegative element. You see, this is 180 degrees, so they are cancelling out. If they are cancelling out, this guy is completely non-polar. So this means CO2 is the least polar. So let's look at our answer and see if we can nullify. We have to start from the least to the most. So the answer is either A or C. All right, so now let's consider the next structure. So if you consider alcohols are very polar, just like H2O is polar. So this would be the Lewis structure of your alcohol. You see how you have 2 lone pairs? This part looks like an OH of water. So definitely alcohols are polar. And we can again justify by drawing our dipole moments pointed towards the most electronegative, which means electrons are residing next to the oxygen more than the hydrogen. So they will be partially positive. The oxygen will be partially negative because it receives the electron density from the carbon and the hydrogen. So it's polar. Okay. And of course, if you put 2 of these, you expect hydrogen bonding. This will just be London dispersion forces. This and of course, you'll also have what we call dipole. But dipoles are not strong intermolecular forces compared to hydrogen bonding here. So that can also tell you that methanol alcohols are more polar. So you already now know the answer, because now this means that the second in rank will be the, let me draw it here, will be the fluoromethane. Okay, this will be the Lewis structure of CFH3. Fluorine is very electronegative, so it does have dipole moments pointed towards it. So this makes fluorine partially negative, and the carbon that is less electron dense partially positive. You have some polarity, but it's only by dipole. And the good thing is these dipoles are not cancelling out like you saw here. CO2 also has dipoles, but they cancel out. This one does not. So if you are to rank, CO2 will be the least. Okay. followed by CFH3, and then followed by your methanol. Methanol will be the most polar. So that is what we were looking for. All right, so let's continue with the next question, which is question number 1-4. How many energy level shells does cesium atom contain? So that's a periodic table question. I think it should be in period 6. You see it's right here. It's in the 6th period. It's right here. So that goes with the number of shells it should have. Like six circles across outside the nucleus. So what happened here? Yeah, so the answer here is 6. How many electron domains are on the nitrogen atom labeled C? Okay, so I'm just gonna draw the snippet of that part of the molecule. Again, this nitrogen has no formal charge, so we have implied lone pair that you need to show, and that tells you have 3 electron domains. You have a double bond, you have a lone pair, and you have a single bond, and therefore the answer is 3, option A. Okay, next is a resonance question. Question 16 is resonance, so we're going to just push the 2 electrons from the pi bond towards the area where there is less electron density, and that's evidenced by the presence of a positive charge. You do not push the electrons this way, you push the electrons towards the positive charge because electrons are negatively charged. Opposite charges attract. So that's how you can quickly predict the resonance product. Okay, so we will do that and put a plus charge on here. So this structure right here is resonance structure B. So the answer is resonance structure B, which happens to be answer B for me. For you, could have been ordered differently. So this resonance structure B is the answer. So now next, 17. I think you know the answer to 17. It was an easy one. 17 says, what intermolecular force of attraction would exist between 2 molecules of 2,4-dimethylpentane? That's an alkane. Alkanes will definitely have London dispersion forces. So 2,4, 1, 2, the metal is here, 3, 4 here. So 2,4-dimethylpentane. Alkanes, alkenes, alkynes. In fact, let me just say in simple terms, whenever you have hydrocarbons, you know what hydrocarbons are. Those are structures that only have hydrogen and carbon in them. Hydrocarbons will have London dispersion forces because there's really no dipole or hydrogen bonding that can happen within the structure. So that was simple. I told you that one, you should have gotten it right. Let's look at it in how many lone pairs of electrons are in the Lewis structures of P, B, R3. So again, follow through the steps of drawing the Lewis structure and then include all your lone pairs possible. You'll find that if you count the lone pairs, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So the answer is 10 lone pair of electrons for question 18. Next, we do question 19. Let's do question 19. What is the maximum number of electrons that can fill up a p orbital? You know that it's 6, because each orbital takes a maximum of 2, and those electrons have opposite spins. So that means that you singly populate these orbitals of the rooms and then pair them up. You count all of them, it turns out there's gonna be 6 of them in there. All right, simple as that. And then we do the next question, number 20. Is there question 20 or that was the last one? Oh, question 20, you have to give the name to this snake. Let's see if I can draw it. Okay, so that's the chain length that we have to label. So I might start from the left, and I'm tracking my longest chain. Okay. Alternatively, you could number from the other side. Make sure not to skip any carbon, because then you're gonna be so wrong. There should be 11 carbons in the longest chain. Notice that you could have also numbered from there, which would make this the substituent. But these are my substituent for now. I do have a methyl, and this other substituent here is called isopropyl. So the rule is you have to give your substituents the least locant position possible. In which case, I would rather, you see, before I tell you why I choose whichever, the shortcut that we used in class, we said we sum them up. So you have a methyl R2. Let me see. Let's start with the blue one. The blue numbering system. Come on, pen. So you have a methyl at 2 and you have isopropyl at 7. If you sum these up, the answer is 9 for the locant positions. And then on the white, with the white numbering, I have a substituent at a methyl at 10, and I have the isopropyl at 5. I sum it up, I get 15. So obviously the blue numbering is correct, the white numbering is wrong, because it's giving us a higher sum for the location of the substituent. That's what we call the locant position. And now I'm going to just focus on the blue numbering. So it means my name should have 2 methyl, not 2 methyl, because now you have to consider I and M. Who comes before who? I comes before M in the alphabet. So the name of this molecule should really start with the isopropyl. So it's on the 7th position. So it's 7 isopropyl, or isopropyl, the British way of saying it, isopropyl, and then 2 methyl. Okay, and now you have the chance to give the long name. It's 11 carbons, so we use un, like in French, do, tra, or does counting. So un, and then it's undec, that refers to 11. It's an alkane, no double bond, so the suffix name should be A-N-E, undecane. So the answer is 7 isopropyl 2 methyl undecane. From on my side, you know, your answers might be scrambled, but the answer here on my side happens to be choice B for me. The main point is not even really the alphabet, it's the answer itself. 7 isopropyl 2 methyl undecane. All right, so let's see. Question 21, which I think is the last one. Question 21 for exam 1 you need to provide the UPAC name. So here it's an alkene, so I'm gonna prioritize the position of the double bond. So if you start from this side, that will be your numbering, but if you start from the other side, you see, comparing 3 and 5, because you have to prioritize the position of a double bond. Comparing 3 and 5, the white wins. So forget about the blue, because the white numbering gives you the least number position. The first time you encounter the sp2 carbon of the double bond is 3, but with the blue it's 5, so the 3 wins. We don't prioritize the substituent. If you go with the blue, that would mean that you're prioritizing the position of the substituent, but in alkenes and alkynes you prioritize the position of the double bond or triple bond, unless that does not help. Then you go to the second rule, which is the substituents. If that does not help, you use alphabet rule. Okay, so anyway, we do have 2 metal groups. We have a metal group here and we have a metal group here, and we are going with the white. So you have metal group on 3 and you have a metal group on 6. So in which case we have to say dimethyl. So the name will be 3,6-dimethylheptene, which specifies the position of the double bond. Okay. Next, question 22. Let me just widen it, because this will just specify the name of the, it's talking about this drug which is used in chemotherapy. It's Taxol. Identify function groups A through D. So A is an amide, B is alcohol, that's an ester. You see CO carbonyl C, that's amide, and then COC, that's ether. So the correct answer was amide, alcohol, ester, then ether. And then the next one, which one can rearrange out of this? Let's see if I can explain that on here. Which of the following carbocations cannot rearrange hydrogen shift to be more stable? Okay, so carbocations are ones that have a C+. So like this is tertiary, because you have 3 carbons around the C+. This is secondary, 2 carbons around the C+, and this is primary, 1 carbon around the C+. And then of course where you have CH3s, that's just called the methyl. The way I've written them right now, the tertiary is more stable than secondary, secondary more stable than primary, primary more stable than methyl. Alright, so usually carbocations like to do shifts to be more stable. So for example here, A is a secondary. You see, I see a carbon here, I see a carbon here, but I also have hydrogens that are not shown. So let me use that, and let me use this color for this hydrogen. So I can move this hydrogen to where the plus sign is, and that's what we call the H shift. So that's what the question is talking about, hydrogen shift. And if you move that, the carbon on the other side will be 1 bond less. Okay, so you're gonna end up with this structure. The plus sign will come here. The hydrogen that moved will neutralize the plus charge. So basically this structure can be simply drawn like this without showing the hydrogens. Now it has become tertiary and it's more stable than how it was secondary. So A can rearrange. So that's not the answer. The question is, which of the following cannot rearrange to be more stable? So this can do it. So that can do it. And then now let's look at B. Can B rearrange to be more stable? So for B, it's already a tertiary. You see, this is already a tertiary. It does not need to rearrange. So this one cannot. And that probably will be our answer. And then C. C is a primary. The C plus connected to one other carbon, so I can make it secondary, which is better than primary. So just move over hydrogen like we did before. You know, you do have two hydrogens here. They're just not drawn, but they're there. After the shift, you'll have three hydrogens. The plus charge is gone because now the carbon has 4 bonds. This carbon will have 4 bonds around it. But now you'll be left with one hydrogen. Now this becomes secondary carbocation. Can be drawn simply like this. That's secondary. So it's more stable than the primary. So this one can rearrange to be more stable. And then let's see. The next one is let me squeeze D here. Yeah, D is also a primary, so the primary can rearrange. There's a hydrogen here. If you do the shift, you're just exchanging positions with hydrogen and plus sign. You're gonna end up with tertiaries that can rearrange. So the answer was structure B. It's already tertiary. It cannot rearrange to be more stable than before. All right. Let me insert page. Let's see. Okay, let's proceed with our review. We are on question 24. This is called Anti-Macovinic of Addition. So basically, when you're given these reagents, the hydrogen goes where there is less, and then the OH from the reagent will go where there is more hydrogens. Usually, it should have been the other way around for Macovinic of addition, but this is called Anti-Macovinic of addition. You can review that in your slides. So the product here will be like this. So there's going to be a hydrogen here, and there's going to be OH there, and going to be a metal. How would you know that we are adding H and OH? I told you when I taught you this, that when you see BH3, sodium hydroxide and peroxide, you should be adding H and OH, but in anti-Macovinic of fashion. So the answer here is A. On 25, which one is the least stable? The hidden information here is looking for 1,3 diaxial interactions. So you know you have a high CH3 there. Count 3 carbons over. There's a hydrogen. There's a hydrogen. So let's assume this is position 1. This will be position 3. Let's assume this is position 1. This will be position 3. Similarly, there's another hydrogen here, which if this is position 3, this will be position 1. 1, 2, 3. So the metal is crowding in space with groups with the hydrogens on the third position with respect to itself. So here the same thing, there's crowding between the tertiary group and the hydrogen on the third carbon. If you count 1, 2, 3, this will be also a third position compared to the isobutyl. So the hydrogen that's down there is crowded with the metal. So you have too much 1,3 diaxial. That's why we call them 1,3 diaxial. You just count 3 carbons over, look for a group that is crowding in space. So 1,3 diaxial interactions, it's crowding. Molecules don't like things crowding on them. So molecule A has a lot of them compared to B, C, and D. So the answer is structure A. And that ends the review for exam 1. Watch out for the review for exam 2.